Hello everyone, this is Rakshit. I am from Sri Venkateswara College of Engineering. Today I am going to present on continuity equation in Cartesian coordinates and Bernoulli equation. First we will discuss about continuity equation in Cartesian coordinates. Definition of the continuity equation in Cartesian coordinates is the continuity equation is an expression of a fundamental conservation principle, namely that of mass conservation. It is the statement that fluid mass is conserved. All fluid particles that flow into any fluid region must flow out. To obtain this equation for three-dimensional flow of the component is del u by del x plus del v by del y plus del w by del z is equal to 0. Equation for two-dimensional flow of the component is del u by del x plus del v by del y is equal to 0. Now we will discuss on derivation for continuity equation in Cartesian coordinates. Consider a fluid element of length dx, dy, dz in the direction of x, y and z. Let u, v, w are the inlet velocities components in x, y and z directions respectively. The mass of fluid entering the ABCD per second is, which means the mass of fluid which enters in this direction is equal to density into area of ABCD into velocity in x direction. The density we will know that there is rho into area of ABCD means dy into dz. The velocity in x direction is u. We will multiply this all the equation, we will get rho u dy dz. Like that, the mass of fluid leaving the phase of EFGH, which means the phase leaving in this direction, we will get the equation as same equation like, but the small change is rho into u into dy into dz plus different partial differentiation of this rho u dy into dz. The expression we get as rho u dy dz plus partial differentiation of with respect to x as rho u dy dz. Next, the net gain in x directions is rho into u into dy into dz minus rho into u into dy into dz minus of del by del x of rho u dy dz with respect to x. By this we get rho u dy dz minus rho u dy dz minus partial differentiation of rho u dy dz with respect to x. Rho u dy dz minus rho u dy dz will be cancelled out, which means the mass of fluid entering ABCD minus mass of fluid leaving in EFGH. Therefore, the net gain in x direction is minus this one value minus del by del x of rho u dy dz with respect to x. Similarly, the net gain in y direction and z direction as minus del by del y with respect to rho v dx dy dz, and in the z direction is minus del by del z rho w with respect to x, y and z. The total gain of mass of fluid is minus del by del x of rho u dy dx dz dy minus del by del y of rho v dx dy dz minus del by del z of rho w with respect to x, y and z. In this equation we will take the common as dx, dy and dz. We obtain this equation. Since the mass is neither created nor be destroyed in the fluid element, the increase of mass per unit time in the fluid element must be equal to the rate of increase of mass of fluid in element. But the mass of fluid element in rho dx divide dz, and its rate of increase with time is partial differentiation with respect to t. Therefore, we obtained as del p by del t into del x into del y into del z. By these two equations, A and B, we will obtain the equation del by del x into rho u plus del by del y into rho v plus del by del z into rho w into dx divide dz is equals to del rho by del t into del x del y del z. Del x del y del z is common in both LHS and RHS. We will cancel it. We got the equation as del rho u by del x plus del rho v by del y plus del rho w by del z plus del p by del t is equals to 0. This is the equation for Cartesian coordinates. Continuity equation for steady flow. For steady flow, we know that del p by del t is equals to 0. Since this equation becomes del rho u by del x plus del rho v by del y plus del rho w by del z is equals to 0. In this above equation, the rho is common. Therefore, del u by del x plus del v by del y plus del w by del z is equals to 0. And the rho we will send to the RHS. The equation becomes del u by del x plus del v by del y plus del w by del z is equals to 0. This is the equation for continuity equation of 3-dimensional. But for 2-dimensional flow is the component w is equals to 0. Hence we got the expression as del u by del x plus del v by del y plus is equals to 0. Next we move on to Bernoulli's equation. The definition of the Bernoulli's equation of the motion is Euler's equation of motion for a steady flow in an ideal fluid along a streamline is a relationship between the flowing fluid's velocities, pressure and density. It is based on the Newton's second law of motion, which asserts that linear moment is preserved without an external force. The expression for Bernoulli's equation is v square by 2g plus p by rho g plus z is equals to c. The assumptions made in the derivation of Bernoulli's equation is the fluid is ideal, that is viscosity is 0. The flow is steady, the flow is incompressible, the flow is irrotational. The derivation for Bernoulli's equation is consider a streamline in which the flow is taking place in the direction of S as shown in the figure. The direction is here. Consider a cylindrical element of cross section dA and length ds. This is dA and this is ds. The force acting on the cylindrical elements are pressure force. Pressure force is acting, that is P into dA in the direction of flow. The pressure force is acting as a P plus del P by del S into ds with respect to dA, the opposite direction of flow. And the self weight is acting rho g into dA into ds. Let theta is the angle between the direction of flow and the line of action of the weight of the element. The expression for this equation is resultant force of the fluid element in the direction of S is equals to mass of fluid element into acceleration in the direction of S. As we know that the resultant of fluid element is all addition of all these expressions, so we get PdA minus rho g dA ds cos theta minus P plus del P by del S into ds into dA is equal to rho dA ds into acceleration, which is taken as A into S, where acceleration in the direction of S is given by V into with respect to V into del V by del S. Equation 1 becomes PdA minus rho GD A ds cos theta minus PdA minus del P by del S ds into dA is equals to PdA into ds into V into del V by del S. Here PdA and here PdA will be cancelled. Finally, we got equation as minus rho G dA ds cos theta minus del P by del S ds dA is equals to P dA ds into V del V by del S. Now we will divide rho dA ds on both sides. We will get expression as minus g cos theta minus 1 by rho del P by del S is equals to V del V by del S. Consider these equations should be sent to RHS. We will get as positive g cos theta plus 1 by rho del P by del S plus V del V by del S is equals to 0. This is equation B. From figure, cos theta is equals to del Z by del S. Therefore, the above expression becomes as g into dz by ds plus 1 by rho del P by del S plus V into del V by del S is equals to 0. Divide ds or del S, anything is okay, on both sides. We will get as g into dz plus del P by del rho plus V into del V is equals to 0. The above equation is known as Euler's equation of motion. But the Bernoulli equation is obtained by integrating the Euler's equation of motion, such as integration of g into dz plus integration of del P by rho plus integration of V into dV is equals to constant. Constant is obtained by integration constant. The integration of g into dz means g into z plus integration of del P by rho means P by rho plus integration of V into dV means V square by 2 is equals to C, which means constant. Now divide G on both sides. We will get expression as Z plus P by rho G plus V square by 2G is equals to C. V square by 2G plus P by rho G plus Z is equals to C. Hence, it is proved where the expression is V, in the expression V square by 2G is equals to kinetic energy per unit weight, which is kinetic head. P by rho G is pressure energy per unit weight of fluid or pressure head. Z is potential energy per unit weight of fluid or potential head. Thank you for watching my video.